So this work has been going on at NEXTOR for over the past 2-3 years, I would say. And the people who deserve a lot of the credit here are my colleagues at Virginia Tech, Tao Li, Thomas Spencer, Nicholas Sikas, and Yang Zhang. They have contributed in some parts of this. Of course, we also have to thank the support of people at the FAA, specifically Thea Graham, Dave Chin, Joe Post, John Goulding, and of course, Ashwin Gunam, who now is working with Thea, but he works at GRA, who co-developed the original, one of the original versions of this particular model that I'm going to describe to you here. So the presentation here goes to the motivation, and then we show you some of the simulation results. As Arnie mentioned, the aviation system is very safe, but if you think about it, there is about maybe 500,000 flights every year, depends on how you count, of flights that go across the oceans, whether it's the Atlantic or the Pacific Ocean, that originates or ends in the US, and also in many other parts of the world like South America, Canada, etc. So of course, measuring the benefits of advanced technologies in oceanic airspace is something that certainly the FAA seems to be very interested, as well as other air navigation service providers like NAV Canada, NATS UK, and others. So the objectives here was to develop a model which really the effort started as a validation of another model, but then the model took an organic form in its own. So the idea here is to estimate what are the fuel savings, travel times, and other measures of level of service that we can infer from this oceanic capability that will be deployed in the future if more precise navigation and surveillance is actually implemented or deployed. So again, this is a topic that both FAA and ICAO certainly have great interest. Here you see this is just for the Atlantic region. You see some examples of the number of flights that cross the Atlantic every day in the organized track system. Depends on which day you pick and how you count those flights, maybe somewhere between 500 to 600 every day in a 24-hour period. However, there's a lot more flights on the South region which are not going to be flying the organized track system. These are called non-OTS flights in my presentation. Similarly, you have flights from the West Coast to Europe. Those flights typically follow non-OTS routes. They are user-preferred routes, and these are random flights sometimes, as they are called. So we are going to be describing how is that we measure the benefits for each one of these types of flights. These are some of the improvements that we can get with better technology, better surveillance technology, or space-based ADS-B, for example, being one of the technologies. You can reduce longitudinal separation in trail inside the OTS. You can also reduce lateral separation between the tracks. You can also reduce lateral separation for non-OTS flights. And of course, if we have better surveillance, we can allow more planes to actually execute climbs, which during the busy periods right now, we don't see a lot of climbs in the OTS. So the idea here was to develop a model, and this model should obviously is fed through real data, like for example, TFMS data at the bottom here, or we can actually make our own flight plans. Because if you don't have data, or if you are predicting the future and you want to add another 40% more flights than the baseline scenario, then we have to start predicting the future, and that means creating flight tracks ourselves, or flight plans. So we have a model that is able to do both, to take TFMS data, as well as to do its own flight planning, and then we basically inject it into a simulation model. The simulation model uses the Eurocontrol BADA aircraft performance is tweaked, actually, because we have a lot of good data that Mr. Heimlich sent us from A4A. And by the way, great thanks to the A4A folks, because they have provided very nice data. As you can see, each one of the boxes here that are in green happen to be data inputs that the model uses in some way. For example, the A4A data is there primarily to calibrate some of the behaviors in takeoff mass that we have across the Atlantic or across the Pacific, for those flights. This model is basically a numerical time-step simulation model, perhaps similar to TAM or RAMS for those of you who are familiar with those. We have conflict resolution and detection, but the model also has some components. If you look at the very center of this, and I wish this pointer actually, I was using the pointer in the wrong way, excuse me. So the flight planning function here, under the flight planning, the track assignment is actually an optimization algorithm. This is the reason why we decided to develop this almost from scratch, because it's very difficult to do optimizations in existing models like TAM or RAMS, where you will have to have a bus structure that passes parameters out of the model. You do your optimization, and then you fed it back. But anyway, let me give you, again, some of the ideas. So here we have an airplane that is flying over the ocean. So we have some basic differential equations of motion of this aircraft, and we basically sample the position of the plane every 5 seconds. So every 5 seconds, we recompute the fuel flow. We put it back into these equations of motion to recalculate the mass. We have also behaviors in terms of the aerodynamic behavior of the aircraft, and then we can calculate distance, mass, and altitude, which are going to be the state variables in the model. Now, of course, if this vehicle encounters another vehicle and you have to separate it, then we obviously trigger some action, and you will see that we have some rules for that. We also have this model communicating behaviors between pilots and controllers, because remember, in oceanic areas, right now there is a lot of data link communication that goes on. So part of the analysis that we want to do, we want to keep track of how many messages are being sent from the plane to the air traffic control people, and that way we can capture some perhaps precursor measures of workload, or, for example, we can count how many times the pilot attempted a climb and it was denied, perhaps due to traffic considerations and so on. So we have all that dynamic capture there. Now, these are some of the things that we have to explain, because the model really is two separate behaviors. The behavior in the organized track system is very different than the behavior elsewhere, because in the OTS, you have a very, very rigid way of doing business. However, we use basically Mach number control and variable headway control rules. Depends on your target Mach numbers that you have, and we have to make sure that those separations are going to be good. On the other hand, for non-OTS flights, we basically we have more freedom, more degrees of freedom, and we can change flight level, we can change the Mach number, or we can detour the plane. Notice that we also have two conflict rules. One is strategic. As soon as the plane enters the oceanic area, as shown here, for this flight that goes from Quito to London Heathrow Airport, immediately the controllers in the Oceanic Center, in this case in New York, will start querying this flight against other flights to determine if that's going to be a conflict ahead. Typically, sometimes those conflicts can be detected by the system 1 or even 1.5 hours ahead of time. However, because of the wind conditions are uncertain here, as the vehicle approaches another vehicle, you have to trigger a tactical conflict and resolution algorithm. So in this model, we have both of these. Let me show you some of the things that we produce. So this model produces things like, for example, fuel consumption, travel time, of course, because these are two key metrics. But we also predict, what is the percent of the flights, for example, that are going to be given, they're accommodated in the track and the cruise flight level that they are requesting in the organized track system. For the non-OTS flights, we can also find what is the percent of the flights that get affected by these conflict resolutions, whether they are tactical or strategic. So again, these are measures of performance of the system, is that right? So we want to do that. And of course, we can also track the number of pilot ATC exchanges. For example, when the pilot requests a climb, and whether that climb is denied, we obviously log that in. And of course, you also get a flight trajectory that can be as detailed as every 5 seconds if you want it. Perhaps for a safety analysis later on. This is an example of an actual animation. This is a screen capture of a post-processor that we have to be able to, this is just for the Atlantic. You can see the 4 big regions, Gander, Shanwick, New York, and Santa Maria. And here we have a west flow condition for that particular day. It's very difficult to see, but there is actually tracks shown in blue. So you don't see that very well unless I really dim the lights, but I don't want to put people to sleep. And of course, as you see here, the organized track system is very rigid. However, there is also hundreds of flights that are not using the organized track system. So the model is able to do both of these. We obviously have to validate this. Is this model really telling us the truth? And again, Mr. Heimlich from A4A gave us very nice data that we can use to be able to compare. Remember, we are still subject to the VADA model in terms of the accuracy. However, it's nice to see, for example, that when we model and this aircraft remains to be unnamed, but you probably can make up who this airplane is. This is a twin-engine wide-body aircraft. This basically shows me the behavior of eastbound and westbound flights, and this is the A4A data. And in general, we are within 2 to 3% of what A4A statistics, for those OD pairs that we collected. So that's good. I mean, that's good news. Let me show you some preliminary results of these. And I would put the caveat here. These are still preliminary because we continue tweaking this model. These are some of the assumptions that we made. For example, we model, in these results that I'm going to present, we model both the Atlantic and the Pacific Ocean flights. We are basically modeling 21 distinct aircraft, including the new generation airplanes like the Dreamliner and the 747-8. We had 3 days of demand that we basically took from TFMS and we injected into the model. We're using 2,000-foot hemispherical rules. And again, I don't show the results in terms of dollars, but I show the results in terms of millions of kilograms of fuel saved every year. But again, there's also some equipage level here that was conducted by a survey done by FAA and CSSI some years ago, and I understand that that is also being updated. So here are some of the early results. This is for the Atlantic side. You see here the model. We ran the model for 3 days. That implies about 2,349 flights, including New York oceanic flights and also the flights inside the waters area. And we basically see here, you see the breakdown between tactical conflicts and strategic conflicts. Right now, the model seems to be resolving a lot of these strategically. And again, we have to go back to the actual data from ATOP to find out whether or not that is true. We visited New York Center, and we found that they are very strategic. They try to solve these conflicts very, very early on so that they don't have to worry about for the next half an hour or for the next hour. So again, this is what the model right now is showing us. Now, in terms of the tactical things that happen when you have to now start doing minute adjustments to Mach number, for example, to be able to deconflict 2 planes that are nearby, these are some of the results that we see. Here we show 3 scenarios. Right now, we assume that the baseline, if you are not equipped in the ocean, you're going to be separated to a minimum of 50 nautical miles. If you are equipped, 2 airplanes that are equipped today, they could be as low as 30 miles. Now, we are also investigating a more advanced scenario where we could have 15 nautical miles separation between the 2 targets if they are properly equipped. So again, what you see here is that these are the number of Mach number changes that were produced in the model as these tactical decisions were made. And you can see here the obvious trend. When you have a large separation, there is more things happening. And of course, specifically, you want to take a look at these blue lines or the blue trend, because that happens to be the high. Well, we changed the Mach number up to Mach 0.02 for most of these flights. That's the upper limit that we put. If that resolution strategy doesn't work, then we have to do a lateral adjustment probably, because that would be perhaps more appropriate. So a lot of these behaviors, they have to be, again, calibrated against real rules that oceanic controllers will use. And we visit the New York Center and Oakland Center to learn from them. These are examples of also the tactical resolutions, but in this case, we're looking at changes in cruise altitude. So for example, here, 76% of the flights in the baseline scenario were able to pick the altitude. They were able to stay in the altitude that they requested. However, you can see that as the separation criteria reduces or is reduced, then up to 89% or 88.9% of those flights will actually stay in the flight level. So this is a big improvement. Doesn't seem like a big improvement, but in terms of fuel consumption, it really pays off. So here are the numbers. I mean, again, preliminary numbers. When you look at Atlantic flights, if we go from 50, which is the baseline separation, to 30, then we get about 91 kilograms of fuel saved in the Atlantic, 81 in the Pacific. And you can see that these numbers are almost, not exactly twice these numbers, because again, these conflicts are fairly random. Nevertheless, for Pacific flights, which are fairly long flights, you get a gain of about 173 kilos. That's about 400 pounds per flight. Now, of course, the question is, how much is that? Well, these are greenhouse gases, by the way, that we just put out as a multiplier of the fuel. Now, what happens in the OTS? In the OTS, we examine the situation, again, by looking at these particular headways between these flights. And then when there is an opening like shown here, if there is a flight below that wants to climb, that flight is able to climb if it satisfies certain dynamic rules. By the way, another reason why this model is slightly different than TAM or than RAMS is that every time that this cruise flight level change is made, we are recomputing basically the fuel burn all the way up to the destination. So we have a pseudo optimization being done for every flight. And that takes a toll. This model takes about 6 hours to run on an i7 machine right now with about 2,300 flights in 3 days. So that gives you an idea of the level of computations that go on. In the OTS, we factor that if we could reduce the separation criteria to 2 minutes in trail, which obviously is a very aggressive target, we could probably see, allowing climbs in the OTS, we will be able to see a benefit of about 158 kilograms. And by the way, I put all in metric here because I was told, even when I was studying my undergraduate, that FAA was going to be metric 25 years ago. So I'm trying to contribute a little bit to that effect, is that right? We'll see. So anyway, these are examples of the comparison between the OTS versus the non-OTS flights. And you can see that the numbers are quite comparable. Going to the 15 nautical mile separation, 2 minutes of reduced longitudinal separation is almost equivalent to 15 nautical miles. Depends on how fast you fly, but at Mach 0.8 is probably around 16 nautical miles in trail. So they are quite equivalent. And again, this number here for the OTS flights includes savings that are achieved through the climbing procedure, okay, inside the OTS. This is for the numerical simulation, this is our fleet mix, just to show you the types of aircraft that were considered. The reason why you see large numbers of 737s and Airbus A320s here is because all of these guys belong in the waters area, okay? And remember, we are also modeling in the Atlantic that specific area called waters. When you extrapolate these numbers and you try to annualize, how much benefit do we get? Well, somewhere between $43 to $55 million annually. Again, if you consider, if you go from the baseline, which is 50 nautical miles to 30, and then on to 15. So again, these numbers are still preliminary, but that gives you a sort of a ballpark of what the model is capturing, is right? So as a conclusion, I would like to, well, first of all, sort of echo what Mike Ball said this morning. It's always a pleasure to work with hardworking and intelligent students, really, at our universities, and that's probably one of the conclusions that I didn't put here, but I should. And of course, we have developed a simulation model that can estimate these benefits. The hope is that this model can be used by agencies or organizations like FAA and ICAO for decision-making in the future, as you guys make all these hard decisions about whether to invest in that technology or not. And again, I just put here with the caveat that these are still preliminary results, that for Atlantic flights, we're looking at maybe 150 kilograms per flight on both areas, the non-OTS as well as the OTS, so almost very similar numbers. And then for the Pacific Ocean flights, where one would expect a lot more benefits, nevertheless, the Pacific flights turn out that there is a lot less density of traffic, and there's fewer conflicts that occur already in the Pacific today. So anyway, the benefits are about 171 kilos. And when you extrapolate these numbers to an annualized basis, you get numbers on the order of $43 to $55 million. And for the OTS, that is equivalent to about 37 million kilograms. Because remember, in the OTS, we only get about 50% of the total traffic that goes across the Atlantic inside the OTS. In fact, the numbers, the more recent numbers, even point out that fewer than 50% of the flights are actually using the organized track system. So this was my last slide. I have a few backup slides, but since I finished early, Mike, you didn't give me the 5. So that means I'm early, so you are free to ask me any questions.
So far, it's been a great event here to be here at the event and speaking. My only complaint so far is the relative height of this podium, which not only do I not like when I'm up here, but sitting where I am down there, I haven't even been able to, only Mike Ball, I'm the only one I've been able to see, really. But other than that, it's a pleasure. And really, like everyone has been saying, but I want to make my special gratitude on behalf of my Purdue colleagues that have worked on NEXTOR 2 projects, that we're very pleased to be part of this family. And I use that term because it has, since we were able to join, it has been a very family-like atmosphere. We've really enjoyed it. Besides myself, Professor Landry and Ding-Feng Sun and Murray Crossley, et cetera, have sort of been involved, and it's really, starting with Dave Chin, really appreciate that, that support and that leadership at Dave's level for making that atmosphere, and then to Mike for the herding of cats problem that he's done masterfully. So my presentation today is hopefully going to be, by design, very synergistic with what you just heard from Tony. And let me go to the next slide here. So in summary, as you're kind of reading the bottom line of this presentation, what our goals and motivations are, let me just sort of highlight a few things. First of all, why am I doing this? Well, this has been a very interesting project for me. Kind of my expertise, if I had to sort of look at all the various things I do, is really on modeling and analysis and study of integrated systems. And that started out mostly at the sort of aircraft and technology level and looking at how new complex designs get formed. But really, in recent years, I've really focused also on this system of systems problem. And I don't think I need to belabor the point, although I will on the next slide, about how that's very relevant here. So it turns out one of the bad things about this problem in air transportation and system of systems is that humans are involved. And the worst problem is that organizations are involved. And so what you're going to see in this presentation is really kind of a seed grant study at looking at this difficult problem of economic analysis of investment and how to do the cost and benefits analysis in a way that we can reduce the uncertainty in how these organizations will respond to the kinds of benefits you saw Tony quantify, both from the ANSP side and the operator side. And so really that's our objective there, as you can see, and it really has dovetailed nicely with some PhD work that the student that's been working on this, Ms. Lauren Bowers, has had in mind. And so the opportunity, and I give thanks to Thea Graham for making this possible, to really focus on the North Atlantic as kind of the perfect study to look at these kinds of issues. But really our goal is to say, given this North Atlantic case study and the notion of uncertainty and the structural models of how organizations respond to new opportunities and new technologies, how can we suggest a way to do the economic cost-benefit analysis better into the future? So that's kind of the bottom line up front. So this is where I pound you over the head with what I think we all realize. There's a reason that this slide is complicated, because air transportation system is truly this dramatically difficult. The way we actually use this kind of system of systems framework and notion is to actually try to be very rigorous up front in using this kind of matrix of all the things that are involved, both the physical things, the hardware, the resources, as well as the economics, the operations, and the policies that motivate those organizations that are operating the equipment or doing something with the equipment. So if I were to give you sort of a capsule of sort of what we mean when we say system of systems, it's a collection of systems that are brought together for some unique purpose, but each of which has some operational and managerial independence, okay? So that's the key. These systems are interacting, but it's not like the molecules interacting in your chair, which have the sole purpose for supporting you and giving you a comfortable seat while you nap during my presentation. What this really means is that each of these entities have their own objectives, and so you have to look at the interplay and interdependencies between those. And I have to say the early work done by NEXTOR on CDM was really, you know, groundbreaking in many ways, but really factoring in that notion of how you take objective functions and constraints from these multiple players and try to make them work together. So this is sort of like the backdrop of how we're looking at this specific case of operational improvements and their adoption in the North Atlantic. And so I think it's been a good context. So moving forward to that topic specifically, And we've had some nice benefit in doing this work and looking back at some work that's been done by actually, I think, students that have been involved and faculty in NEXTOR that are now off in great places like the FAA. So Ms. Campus here had put together this sort of notional diagram of stakeholders in the NAT, and you can see circled there are the ones that we're focusing on, the air navigation service providers and commercial operators, but clearly there are others that are at play here. And again, at some point you have to make difficult choices about where do you draw your boundaries in terms of models, either for the performance assessments that you heard Tony talk about or these behavioral issues among the various players. So again, for the relatively modest scope of our project, we're focusing on these two. And so again, another great reason why this is a good example problem is there's an extreme diversity, there's an extreme, relatively speaking, extreme large number of players in this particular airspace. So you see here a list of what I think is a complete list of all the ANSPs that are involved in the North Atlantic. And it's not just the high number, right, but it's the diversity. And by diversity, you know, we don't have a lot of data in the features because I ran out of time. But you can imagine that each of these entities, especially if they're operated as a public or private entity, they have very different structural models of how they make decisions on investment, technology rollout, let alone the operations and the execution of air traffic services. And so this is something we've tried to pay attention to. As you'll see shortly, we're conducting a series of focused interviews, and so we're trying to get a spectrum of each of these kinds of players on the ANSP side in our interviews. Likewise, and I think Tony's presentation already made this quite clear, that there are many operators in the NAT. It's a very valuable airspace for all kinds of reasons. And you can just see some of the sheer numbers of passengers that are, the number of operators and the number of passengers that are being flown by those operators on the upper part of this slide. And on the bottom, you can see also the very significant and important amount of cargo and the number of operators on cargo that are operating here. So my point here, large number of players in this system of systems, and they have a diversity of perspectives, and that's actually been borne out in the interviews we've conducted so far. So again, back to the purpose of the project is not certainly to do a cost-benefit analysis yet, since it's sort of like a one-year effort so far, but really start to look at the processes that have been going on in this area, and there's some very foundational processes and documents on how this takes place in balancing the financial costs with the quality of service and how those play out. And again, you saw even in Tony's presentation and some of the questions that you all raised for Tony, it really depends, as we're going to see, on how the operators perceive the predictability of the benefits that they could obtain, as well as the magnitude of those benefits themselves, in terms of whether they're open to accepting new operational capabilities. And so this is just very basic notion of what we're trying to improve by helping to use this information we're gathering to reduce the uncertainty in those behaviors. So a little bit more deeply here, I think most of you know, probably at least in a cursory fashion, that the purpose of this economic analysis of investment is to say, from whatever stakeholder perspective, is something worth achieving if there's a particular objective, and or if there are several alternative methods of achieving an objective, which of those is best. Probably the first one, depends on the second and vice versa, but these are kind of the basic questions that benefit to cost analysis is concerned with. Now, again, from some of the literature that we've already seen, there's a clear recognition that uncertainty in the time and the magnitude of benefits is important to stakeholders. I don't think that's something that anyone had too much doubt about, but we're trying to understand at the next layer below, what are some of the specific features for the different stakeholders that we can characterize that uncertainty. And on the last bullet, where you see those various sources of uncertainty in investment analysis, we're especially focusing in our study on the human factors, how will operators respond, not only sort of in the cockpit, but the organizations themselves, as well as the information perspective of what's being communicated to whom and when, both on the tactical level and to some extent on the strategic level. And that's probably a good time for me to mention that one of the great parts of kicking off this project is last fall there was a meeting sponsored by NAV Canada up in Montreal where they brought together all of the operators and most all of the ANSPs in the NAT, and there was a workshop in which they sort of talked through these issues that included space-based ADS-B and the concept and availability of that and the perceived benefits, as well as essentially, in my opinion, in layman's terms, especially NAV Canada and such, we're curious why the current ability in the current system that offers increasingly more available flight changes in terms of speed and altitude were not being accepted by the airlines. They were very perplexed by that. And so we were sitting there listening very carefully to some of the reasons that were expressed, and our interviews that we then did subsequently really characterized those more specifically and found some differences between even passenger-carrying airlines, how they perceive those benefits. So kind of the long-term perspective, this work that we're doing to try to characterize these models and the uncertainty in the models of each of the stakeholders could eventually be placed in something like this, which is a conceptual model, but it really is important for showing the flow of the information and how each of the stakeholders would essentially have a version of this transition dynamics process. And a bunch of people contributed to this, and the other nice thing is that many of those people have gone to different places after their MIT work, one of them at Purdue, Dr. Murray. And so I guess there must be an animation here. Yes. Some of the particular things that I've circled in purple are the areas in which our student has focused on the specific categories of questions in the focus surveys that have been conducted based on literature that she's found in terms of, are people aware of the operational improvements and technology available? What are their attitudes towards their adoption in terms of especially cost and benefit? And then what are the current practices that may accelerate or inhibit the adoption given the cost being lower than the benefits, or the balance being appropriate? So the next part of the presentation will really just be giving you a capsule of the, again, in-work preliminary results, as Tony also alluded to, of where we are. So we have these categories of knowledge and awareness, attitude, and practices. And given those, the sort of topics of questioning within those categories have to do with the ability for speed and altitude changes to be provided to flights in the North Atlantic tracks, in the organized tracks. How and when are ANSPs granting those, and how and when are airlines or operators requesting and accepting those? And then the second set of questions had to do with a little bit in the longer term, if something like space-based ADS-B were to come into fruition, provide the increased surveillance, which would give us reduced minima, how would they sort of balance and prioritize the benefits they could get from those things that Tony showed some of them, versus the cost of both equipage and use of that service. We have some open-ended questions at the end on sort of letting them say, how would they, forgetting about what we've asked, what kinds of flexibility would they like to see in the North Atlantic? And part of the reason to have those questions is to support some collaborative work we're doing with MIT and Professor Hansman on that topic. So here we are so far. And as we've been doing anytime we've been presenting this, part of this is showing you what we've done so far, and part of this is twisting arms for people in this room to be interviewed, if appropriate. So we've conducted so far 10 interviews, 5 individuals from operators, 4 from 2 ANSPs, and 1 from a trade association. We're continuing to recruit from pools of candidates, which is what I just said. But we're not sort of intending to sort of solve the space-based ADS-B cost-benefit analysis in this study, but we want to get enough diversity among all of the kinds of stakeholders in terms of number of interviews so that we can do this differentiation that you're going to see in a moment between, okay, is every airline, really prioritizing and valuing the same things to the same degree? Okay, so 2 chunks of results so far preliminary. One, again, on that notion of, in the current system, there's an increasing availability of speed and altitude changes to improve routing. And so how do we see? So first of all, across all the respondents so far, some things have come up in terms of what I call main factors that shouldn't surprise any of you. And consistent with the very compelling statistics as well as complementarity that Arnie provided to all of you about the safety of the system, and how that remains the #1 priority. So we cannot go forward with something unless it's more safe than today. So that was a consistent finding across all the interviews to date. In terms of fuel savings, we see that certainly the ANSPs involved in the NAT, some sort of more aggressively than others, have developed the capability to provide these altitude and flight level changes and speed changes. There should be a mistake. There's a mistake there. Because they feel it's both the benefit of the carriers as well as a fuel savings and reduced emissions for societal benefit. So, that's clearly at the top of their list as a service provider. The airline perspective, you'll see, we clearly see fuel savings as reported as the #1 consideration. My perspective, even after this big meeting up at NAV Canada, is I don't think all of the carriers we've talked to so far know the relative magnitudes that Tony has talked about. Where's Tony? There he is. That gets to this notion of communication that's very important in these transition processes that I think we have evidence here is still probably quite a ways off in terms of where it can be for these particular advantages. Okay, so just a few slides to give you some pictures instead of just words, although we have the quote still here prominently. So again, in terms of operators, fuel economy is #1 for most or many of them. But we did see one of the air carriers as well as cargo carriers saying that schedule reliability is actually a more important factor most often for them to get the passengers where they want to go, to get the connections appropriately achieved and such. And so this was not sort of a blanket rote fuel perspective. There was actually a perspective that said schedule can often be more important in terms of priorities. The ANSPs, in terms of key differences there, clearly we've seen some evidence that some of the ANSPs are more capable and more aggressive and more advanced in offering these flight level changes in the NAT. And again, as Tony mentioned, this is kind of a critical thing that we detected from the carriers that, if you can only get reliable changes that you need when you need them for only a part of the flight that you're operating because of the different ANSP capabilities, this is an issue. And so some of the benefits may be mitigated if you don't have that perspective. And that's kind of the long red quote in a nutshell about harmonization is needed so that we can make sure that these are consistent offerings across the North Atlantic tracks. So another thing besides similarities and differences among the respondents in the different types, we've looked at interdependencies sort of between them, and this sometimes gets to the tactical level as shown here. So kind of again, I think my perspective is that some of the ANSPs up at this meeting we went up to at NAV Canada felt, hey, we've got these offerings to you, and why aren't the airlines and the carriers taking them as much as possible? Certainly there's been a significant uptake in these. It's not like there's no adoption of these possibilities. And again, in the near term, with the developments that have been made, it's been relatively sort of only a change in the operations for the airline. It hasn't been the result of a new equipage other than having to be, the fans 1A equipped, et cetera, et cetera. So airlines are encouraged to request these changes. If ATC can maintain the separation, the new flight level or speed is granted, and this should happen on a regular and almost always basis. The dispatcher plans most optimal routes, and certainly though, as you're going to see in a second, the reality of the real world takes place with the dispatcher, especially on the confidence and the external factors related to this decision. Which brings you to here, and there's a lot to read here, but the bottom line, kind of moving around from the upper right, I guess I'll go counterclockwise. There's a general sentiment by the dispatchers and flight crews that in the past, some of these people and the pilots have been flying the North Atlantic for many, many years, right? So they're well trained, but also used to the environment that they've been flying in. And so there's been an issue of changing the culture, and even if you recognize you need to change the culture, doing that uniformly across an entire carrier and set of pilots takes some time to have confidence that you're going to be granted. From the ATC and the ANSP side, they are finding, as I said, that some are entertaining these greatly while others are not. and they're trying to figure out how to get the others who are not to be more proactive in accepting those and requesting those. And you know, they recognize that for a long time when they were asked for these changes, they were giving the answer of no. So there's this transition process that takes some time. And then finally, the key point there on the dispatch side that came up again in Tony's talk is, and we have some specific interview data on this that I don't have time to go into, but how much fuel is loaded on the aircraft is not an insignificant decision to make. And so, you know, getting the expected changes you need in terms of your flight profile 85% of the time may not be enough for you to reduce that load of fuel, which will get the double effect, as Mike mentioned, of not only reducing the fuel burn, but reducing the weight of the aircraft. So this is probably one of the crux issues, I would say, that we found as part of this difficult transition process. Education, communication, and training and confidence building can help, but it doesn't seem to be there yet at the threshold level. So quickly wrapping up a little bit, we also asked questions about space-based ADS-B as, again, a future capability that would provide even better surveillance and reduce minima and all the benefits you know, that Tony talked about. But it's a little bit farther out, right? And it's also complicated by this system effect where there's, you know, a private operator that's going to be offering the service. Each of the ANSPs may have different motivations and different perceived values to their customers that fly in their airspace for this increased capability. And so all of that is playing out in these assessments of benefits and costs. And we've really found that by actually talking to the human beings representing their human organizations, we're getting some nice perspectives on where they might be thinking about this problem. And actually, we should probably then generate some case studies and scenarios for Tony to run through the model to experiment with what those perspectives would produce. I think that would be something good going forward. So in terms of the operators' key differences, clearly they're concerned, some of them are concerned about the weight-based charges and associated fees that would be placing burdens on certain flights. One of the cargo operators talked about the fact that they're flying sort of against the flow of traffic normally in the NAT, and how does that affect what they're going to be offered or what improvements they can achieve. And yeah, the quote there is just another long quote talking about some of the benefits of the procedural separation going away and creating a more dynamic environment. I think this was a positive, but certainly some people are often less comfortable with a more dynamic environment. So that's something that has to make a play. This was very interesting in terms of ANSP's perspectives. As I mentioned, we saw some differences. Of course, they're organizationally are structured differently, so it should be no surprise. They do obviously see some potential benefits from the ability of space-based ADS-B to provide this increased coverage and essentially broaden the amount of traffic. But we saw things like, you know, how many times is there a flight going from, say, Iceland to Anchorage that doesn't get the desired speed and altitude changes? Almost never. So what's the business case for those particular operators and services in terms of something new? And then, you know, we got a lot of questions from almost every side about what will be really the cost structure that will be associated with space-based ADS-B, and, you know, how will it be priced, and how much can we realize, you know, how much do we have to pay a premium for capability that we may not actually need in terms of frequency and some of the, again, separation minima that Tony talked about. So I'll quickly, let's see, interdependency. So this actually was interesting also. We focused, you know, on talking about the NAT, but many operators especially identified that if they're getting sort of better in the service and the changes and the flexibility they want in the NAT, transitioning to the then domestic airspaces, if that's sort of not in tune with and commensurate with that planning and that process, then we lose many of the benefits, potentially lose many of the benefits that could be achieved. So I really like that quote there. You know, you don't have systematic improvement until you can get all of these pieces working together. And so I think that was a good insight that we can share with the other stakeholders in the system. So again, returning, what we plan to do is take some of these pieces of information for individual stakeholders, differences and similarities, and this is sort of one blow-up version of that process we saw on the last slide. Thank you, Mike. Where we would basically populate in a very qualitative way right now because of the kinds of data we're collecting in terms of focus interviews, and really try to look at these diagrams for each of the stakeholders and ask the questions, you know, how significant are the differences given that one carrier has got fuel on top of schedule versus the other one that has those objectives switch, and how would those objectives actually change the values and the decision making, and then ultimately how would this change the ability in a very simple-minded way to do the cost-benefit analysis on something like space-based ADS-B with a, you know, a distribution on some of these behaviors that's a little tighter than what it normally would be without paying attention to each of the specific types of behaviors in each of these stakeholders. So that's kind of the big picture goal where this could go and part of our work. And unlike the rest of the people who have, of course, said how valuable our graduate students are, I have a picture of a real one in case you imagine that they don't exist, even though many of you in the room probably were one. So Lauren has really benefited from this project, and she's kind of rolling it up into her dissertation, which has kind of a second side looking at the broader issue of stakeholder perceptions of UAS, which I know is of interest, as the administrator said. But really, she's done a good job of balancing this work and some work we're doing also for the FAA through NEXTOR on air connectivity. And we hope we're going to provide a very solid recommendation for a framework for this uncertainty reduction in the cost-benefit analysis and see where it leads from there. So that's my takeaway slide. Thank you very much for your time.